Okay, welcome guys. Here's our first lesson after exam 2. Hope you had fun. So this is what the notes will look like. They're going to be on Microsoft OneNote. I am going to share the link and you should be able to access this. And with that being said, you can download a Word copy or a PDF copy of the notes. They will be blank. So if you can print out this page, that's great, because this is where I'll write everything down, or even better, write it down yourself. There you go. Okay, so the reason we start off with 6.2 before we get into section 8.1 is we want to do a refresher on what one-to-one functions and inverses are, because that's what 8.1 is all about. 8.1 is all about inverses. Okay, inverse trig functions at that. So let's do 6.2. This shouldn't take too long, and then we can jump into 8.1. I'll make a separate video though. Okay. Okay, so determine whether a function is one-to-one. A function is one-to-one if any two different inputs in the domain correspond to two different outputs in the range. That is, if x1 and x2 are two different inputs of a function, then f is 1 to f. F is 1-to-1 if the y value of x1, so the y value of x1 does not equal the y value of x2. That's what it means to be one-to-one. To be one-to-one, simply put, every x has one y and only one y in the range. Okay, so the blobs below show what a one-to-one function is, and the very first blob here is a one-to-one function. We see that x goes to y1, x2 goes to y2, x3 goes to y3. Every x has one and only one y. This is what it's meant to mean. This is what it means to be a one-to-one function. Okay? All right. Second picture. It is not a one-to-one function because x1 goes to y1 and x2 goes to y1. So this is a function, but it's not one-to-one. To be one-to-one, every x must have its own y. So this is not a one-to-one function. Okay. And then the third one is just not a function at all. You see that one x value goes to two y values. That does not represent a function, and that definitely does not represent a one-to-one function. So what we're going to focusing on today in 6.2 and in 8.1 are one-to-one functions. That's what we're looking for. Okay, with that being said, example 1 down below, we just want to know is the set of points a one-to-one function. So the first set of points is -2, 6, -1, 3, 0, 2, 1, 5, 2, 8. So first, we see that no x values are repeated. And second, we see that no y values are repeated. So this means for this set of numbers, every x has its own y. So this means that the first one is a one-to-one function. So yes, it's one-to-one. Now the second set of coordinates, 2 goes to 6, -3 goes to 6, 4 goes to 9, 1 goes to 10. Well, we already see our issue here. 2, 6, -3, 6. We have two different x values going to the same y value. So this, yes, is a function, but it is not one-to-one. So, no. Okay, so again, to be one-to-one, every x has exactly one and only one y in the range. Okay, so graphically, to see if you have a one-to-one function, we use something called the horizontal line test. So if I graph a function and I draw a line through it, a horizontal line through it, and if I intersect it more than once, it is not one-to-one. So let's take a look at the graph of x squared. We know that x squared is the graph of a parabola, so this opens just like And now, if I were to draw a horizontal line through it, we see that I intersect it twice. And to be a one-to-one function, the horizontal line has to intersect only once. So x squared, unfortunately, is not one-to-one. Not one-to-one. Okay, now the graph of x cubed. Well, x cubed looks like the little curvy S-shaped thing, kind of like that. Okay, there's x cubed. So if I were to draw a horizontal line through this anywhere, we see that I only intersect once. We only intersect the graph once, which means that x cubed is 1, 2, 1. Okay, excellent. So the theorem below says that a function that increases on some interval is a one-to-one function, and a function that decreases on some interval is one-to-one. Well, x cubed is an all-increasing function. So x cubed is always going to be one-to-one. All right. Okay. Determine the inverse of a function. So suppose that f is a one-to-one function. Then to each x in the domain of f, there's exactly one y in the range. That is the definition of being one-to-one. This means that to each y in the range of f, there is exactly one x in the domain. The correspondence from the range of f back to the domain of f is called the inverse function of f. So the symbol f inverse is used to denote the inverse of f. So this is how we find inverses. So if you are a one-to-one function, this means that to go from, let me zoom in on here, zoom in on the blobs. So I'm just going to put an x here and a y there. So to go from x to y, we use f. But then, since this is one-to-one, if I want to get back from y and go back to x, we use the inverse function. And the way to know if you have true inverses is that no matter how you compose them, you should always arrive back at x. So you can test inverses by composing them. And if you arrive back at x, then they are true inverses of each other. Okay. All right. So some things to note about inverses. The domain of f now becomes the range of the inverse. And the range of f now becomes the domain of the inverse. All of that is given above. So if we're going back from y to x, then the range of the original function, as you see here, becomes the domain of the inverse function. And then as we get back to the domain of x, the domain of f becomes the range of the inverse function. So we can essentially say that when you have inverses, their domain and ranges switch. Switch, flip, swap, whatever you want to say. Okay, perfect. Okay, and just like I said above, if you have true inverse of each other, they technically undo each other. So if you were to compose your inverses together, you should always arrive back at x. So you compose them and you arrive back at x. So this is what happens when you compose inverses. All right. And then of course, when you compose, so if f inverse composes with f of x, f inverse has to take the domain of f. So if you put the two functions together, the only way this composed function would work is if it obeys the domain of the domain, if it obeys the domain of the function it's composing with. Same thing here. If f composes with the inverse of f, then f has to take the domain of the inverse. So that's how compositions work. we always take the domain of the function we're composing with. Okay. There we go. All right. So next example is just verify that these functions are inverses of each other. So the only way to do that is to compose them. So we compose them. So I'll call this A. We're going to compose them as G compose G inverse of X. We are composing. Then I get G of G inverse of X. And we know that G inverse of X is the cube root of X. So we plug that in. I get G of the cube root of X. And then I plug that in for X into G of X. So this becomes the cube root of X raised to the third, which gives me X. So we show it one way by composing G with the inverse of G. Since we compose them, we end up with X, which means that, yes, they are inverses of each other. But just to make sure, compose it the other way. So we're going to say B. G inverse of G of X is equal to G inverse of G of X, which means I get G inverse of, and now G of X is X cubed. So that's what we'll put in here. G inverse is X cubed, which means I now get the cube root of X cubed, which gives me X. So composing both ways, G with inverse G or inverse G with G, we still see that we arrive at X. So this means the inverses undo each other, and since we arrive at X, this means that they are true inverses of each other. So that all checks out. Okay. All right. I gotta write it down here, right? So inverses of, whoop. You have to bear with me on this. There we go. There we go. Okay. All right. Next is graphically. So above was algebraically to check for inverses. Down below is to graphically check for inverses. If two functions are inverses of each other, then they will be symmetric about the line y equals x. So here's the line y equals x. And if they are true inverses of each other, they will be symmetric across it, meaning you can reflect points across it. So we see up here, there's A. If I reflect it across the line, you get A prime, or just the symmetric point of A. Same thing, here's B, reflected across, there's B prime. So that's, you could do with any point you wanted. So mainly graphically to check if you have inverses, they must be symmetric about the line y equals x. All right? Okay. Okay, cool. So that's easy. Now we go into how to find an inverse. So I have all these lovely steps above for you. I will work these steps out one by one to solve for the inverse. So that's where we're going to start. So let's just start on the example. And again, this should be stuff you know already. This is just a quick review session. Okay. So first thing we're going to do before we find the inverse is let's go ahead and make an XY chart for x cubed minus 1. So we want to graph these, so that's where we'll start first. So let me bring this down a bit. There you go. So for f of x equals x cubed minus 1, we make an XY chart and pick the most common points to pick when graphing a function. -2, -1, 0, 1, 2. Let's do that. And plug them into x cubed minus 1. That would be -8 minus 1, so that'd be 9, -1 minus 1, 2, minus 1, 0, 8, and 7. Okay, so there's my XY chart. So there we go. We are ready to go. Now let's find the inverse. Where's the most room at? I can do that here. Okay. So now let's find the inverse. Okay. Step 1 to finding the inverse. Change the function into y equals x cubed minus 1. Okay. Step 2 into finding the inverse. Interchange the roles of x and y. So if we go back like 2 pages, when you find the inverse, remember domain and range, which places. And remember, domain is x, y is range. So if the domain and range switch places, this means x and y's always switch places. So step 2 is the important step in finding the inverse because we interchange their roles, right? We interchange their roles. So I'll put it here. Interchange. Which means we just swap x and y. So this becomes x equals y cubed minus 1. That's what we do when we interchange. We swap x and y. Okay. Step 3. Solve for y. Okay. So now I have x equals y cubed minus 1. I add the 1 over. X plus 1 equals y cubed. And then I cube root both sides. And I get the cube root of x plus 1 equal to y. There we go. We have found the inverse. So step 4, we will state it as the inverse. So 4, I'm going to say the inverse is f inverse of x equal to the cube root of x plus 1. Okay, now the above step says to check your work, compose them to see if you got it right. I'm pretty sure we got it right, but if you really want to check, you can compose them yourself, okay? So now, all we want to do is graph this. Well, good thing about graphing is we already have the points. If I scroll back up to the top, here are the coordinates for the original function. So to get the coordinates for the inverse, all you have to do is flip them, swap them, switch them, whatever you want to say. Your coordinates switch. So this means that for my XY chart, -2, -1, 0, 1, 2. This was -9. That was, where was it? -2. That was, if I plugged in 0, I'm not even looking. So everything swaps. -9, -2, -1, 0, 7. There you go. -1, 0, 7. Okay, and let's plot. There we go. So first I'll plot the original function. So -2, -9. -1, -2. 0, -1. 1, 0, and 2, 7. So here's what the original function looks like. So this is f of x. Okay. And then I'll plot the inverse function. So -9, -2, right there. -2, -1, right there. -1, 0, 0, 1, 10, 9, 8, 7, 2. There we go. Terrible. And there is the inverse function. Now, we know these are inverses of each other, and these look pretty symmetric. Well, mine don't, but if you drew them correctly, they would. And these would reflect across the line y equals x. There you go. Okay, that's it. Those are the steps to finding the inverse. So follow those and apply those to trig functions when we get there. Okay, some more practice problems right here. So let's find the inverse, and if you really want, you can check the result. But here, I believe in us. Just find the inverse, okay? And during class time, you can ask me to check the result. I'll do that for you. Okay, so find the inverse of this given function. So number 1, I'm gonna rewrite it as, so step 1, y equals 2x plus 1 over x minus 1. Step 2, interchange, make it x equals 2y plus 1 over y minus 1. Step 3 is to solve, which means that I'm going to take y minus 1 and multiply it to the left side. So this means I get x times y minus 1 equal to 2y plus 1. Now, when we're going through this process, you must remember that we are solving for y. So now on the left side, for x times y minus 1, you are going to do the favorite thing you love to do as a student, as a math student, distribute. You guys love to distribute, so you're going to distribute here, even if it looks wrong. You got to roll with the process. So x and y, x and -1. So we are distributing. So xy minus x equal to 2y plus 1. Okay, remember that you're still solving for y, so put your y terms together. This means 2y is coming to the left side. So I'm going to have xy minus 2y equal to x plus 1. So I moved x over to the right, 2y to the left, and now remember we're still solving for y, so your greatest common factor here on the left side happens to be y. Take out a y. Y times x minus 2 equal to x plus 1, and then divide by x minus 2. And there we go. We have our inverse. Y equals x plus 1 over x minus 2. Now step 4 says state it as the inverse. F inverse of x equals x plus 1 over x minus 2. Done. Okay. There's that. Not a bad process. We do it again. Okay. So first step, y equals 2x over 3x minus 1. That's 2. Step 2, interchange. X equals 2y over 3y minus 1. Step 3, solve for x. Take this, multiply to the left side. X times 3y minus 1 equal to 2y. Distribute. Three xy minus x equal to 2y. Remember, we're solving for y. Put your y terms together. So this means that 2y is coming to the left. 3xy minus 2y equals x. Again, you're solving for y. Greatest common factor is right there. Take a y out. 3x minus 2 equal to x. And then divide by 3x minus 2. And we have our inverse. Step 4, state it as the inverse. There we go. Nothing to it. Again, stuff you should know already. Now, we come to the last page and probably the most important part of this whole notes section. Again, all of this was just a refresher. So on the very first page, we saw that x squared was not 1-to-1, which means it cannot have an inverse. Well, we are able to restrict any function's domain. And if we restrict any function's domain, we can make it have an inverse. So looking at the problem below, x squared plus 1, if we restrict its domain to x greater than or equal to 0, it will have an inverse. Crazy, right? This is how we can apply it to trig functions. Trig functions go on infinitely. Tangent, cosine, sine, all of them go on infinitely, which means none of them have inverses. But if we are able to restrict a trig function's domain, we can make it one-to-one, which means we can give it an inverse. So that's what this is all about. That's what this refresher lesson was all about. Reminding you that we can restrict functions' domains to make them one-to-one, which gives them an inverse. Okay, so let's finish this up. All right, so first thing we want to do, let's go ahead and plot, make an XY chart for the original function. So here's f of x equal to x squared plus 1. Its domain is any x value greater than or equal to 0. So for my XY chart, I have to obey the domain, so I choose anything greater than or equal to 0. 0, 1, 2, 3. That's probably good enough. Plug them into the function, x squared plus 1. This should give me 1. This should give me 2. This should give me 5. And this should give me 10. Okay, awesome. We don't know the range yet, okay? All right, but let's say we were going to plot this already. So let's do that. Let's plot this already. So I'm at 0, 1, 1, 2, 2, 5, and then 3, 10. Here is my new x squared function, which means that it's one-to-one, because if I were to draw a horizontal line through it, I would only intersect it once, which means we have made x squared one-to-one, and it was only possible by restricting its domain. Okay, which means since now x squared plus 1 is one-to-one, we can now find its inverse. So I'll just put here, that's too big. Let me zoom in a bit. X squared plus 1. So we follow the same steps. 1, make it y equals x squared plus 1. And then 2, interchange, x equals y squared plus 1. 3, solve for x. Solve for y. Move the 1 over. X minus 1 equals y squared. Square root both sides. And we end up with plus or minus the square root of x squared, the square root of x minus 1 equal to y. Now, we wonder which sign to pick, plus or minus. Well, the way to determine that is look at the domain of the actual original function. Everything has to be greater than or equal to 0, which means any number we pick, it has to stay positive. So if we come back here to the inverse, the same applies here. We are only going to pick the positive function. So this means that for step 4, we write it as the inverse. One moment, please. Putting this on pause. Okay. So step 4, state it as the inverse, and let's make the XY chart. Okay, just like the other one, take the points, flip them around. There you go. 1, 0, 2, 1, 5, 2, 10, 3. There we go. And let's plot. Okay, 1, 0. A little bigger. 1, 0, 2, 1, 5, 2, 2, 3, 4, 5, and 10, 3. There we go. And there's the inverse of x. And again, these are symmetric about the line y equals x. Okay, before we move on, let's find domain and range. So I'm going to come back to the original function, and if you look at the range, the y value starts at 1 and head towards infinity. So my range here is going to be y is greater than or equal to 1. Okay, and now if we do the range, domain and range for the inverse function, so domain and range, this means all you have to do is take the domain and range from the original function and flip it, switch it, whatever you want to say. So this means that we'll get the domain as x greater than or equal to 1, y greater than or equal to 0. And that's it. Yeah, let me write that in smaller ink. There we go. And there it is. This was a nice refresher on inverses, and now we can apply it to section 8.1. All right, done.